didn't know it was going to set on fire like that, did I? Well, you should have thought about that, shouldn't you? Bloody idiot. Go on, bugger off. I beg your pardon? Sling your hook. Bloody idiot. Unit 2. All right, so welcome back to Andrew Gallimore's Psychedelic Neuroscience Masterclass. You made it through Unit 1, Introduction to Neurobiology. As I said, that was a really important foundational unit, so I hope that you all went through it completely and that you're happy now that you kind of understand those concepts, because those the ideas that we introduced and developed in Unit 1 will be used throughout the rest of the course. So if you haven't been through Unit 1, please do so now, because it's super important. Now, this unit is also extremely important. This unit is actually going to be a bit shorter, but no less important than the previous unit. When at the start of the last unit, I emphasized how information was going to feature a lot in this course, and how important it is that we understand information in order to understand ultimately how psychedelic drugs work. Now, hopefully now you have some intuition as to exactly why that's the case, right? So we spent a large proportion of the last unit talking about how neurons, and thus the brain, generates information, and that the neuron uses this rapid reversal of the membrane potential, the action potential, or the spike, to generate information, and that sequences of these action potentials can be passed via this chemical junction called the synapse to other neurons, and thus neurons can speak to each other, with action potentials being the kind of the language of communication in the brain. So whilst I emphasized this idea that action potentials were the way the brain generates information, I think we should really kind of formalize what we mean by information. You know, why is an action potential informative? Why does it contain information? And to understand that, we need to think about what information is. Okay, so information is it's a kind of a slippery concept. Everyone intuitively understands what I mean by information. No one's thinking, you know, what the fuck's he talking about? Information. You know, it's kind of obvious, right? What information is. You know, it's when you're informed about something. When you learn something, about anything, you gain information. When you reduce your uncertainty about something. What's that bird that's just landed in my garden? Oh, it's a crested whatever, warbler. Is that a bird? Kind of, sounds like a bird. Oh, it's the blue-crested warbler. Oh, you've gained some information now. You know the name about of that bird. And you can learn lots of other things as well. Sticking with the bird thing, you know, you could learn, you know, what's its favorite food? Favorite food? Do they have? I guess they have favorite foods. What does it eat? How long does it live? What color are its eggs? All these things. How much does it weigh normally? Right? These kind of things. So you're gaining information about something, and thus reducing your uncertainty. But that's a little bit vague still. So I think we need to crystallize this concept of what we mean by information, and it's the aim of this brief but important unit to do just that. So information is when we gain knowledge about something and when we reduce the uncertainty about something. We will also think about information in terms of surprise, which is we'll get to in a second, which is kind of an intuitive way of understanding information, I think. Some of you, when I say information, might think of information technology. You might think of computers, and that computers use ones and zeros, right, to generate information. In fact, that's the only kind of information really that computers understand, is these sequences of ones and zeros. Why is the computer able to generate such complex forms of information? You know, the image that you're seeing now is, of course, generated on a computer. And behind the scenes, the computer is shuffling around ones and zeros. And yet, this extremely complex and rich and dynamic pattern of information is what you actually experience. So there's clearly something there that we need to get to grips with, and we'll be using the idea of these ones and zeros, binary code, bits, to get a handle on what information is. Okay, so again, you know, if I asked 10 people what information was, I'd get 10 different definitions, and even if I asked 10 mathematicians or scientists, I'd also get 10 definitions probably, because information can be defined in many ways. We're going to use a very specific definition, which at first might seem kind of a little abstract, and you might think, what's he talking about here? You know, what's this about? But bear with me. It is an apposite definition that will become important as we go through the course. When we get to the mechanism of psychedelic drug action in some of the later units, we will be referring back to this definition. And so it's important it makes sense to you. So I'll kind of try and explain it as best I can and give you a few examples. Okay, so let's start with the definition of information that I'm going to use. So here, so information is generated when a system selects between a finite number of distinct states. Yeah, that seems a little bit abstract, but what do I mean by a system? A system could be anything. It's deliberately vague there. A finite number of distinct states. So let's take the most obvious example of a system that can exist in a finite number of distinct states, a coin. If I was to flip a coin, the coin can land heads up or it can land tails up. The coin is the system. It has two possible states. It can only exist in one state at a time, and when it lands heads up or tails up, it selects one of those states. As the coin is in the air spinning, you have no idea whether it's going to land heads up or tails up. And when it does land either heads up or tails up, you gain some information there. And you also reduce that uncertainty. There was uncertainty as the coin was spinning in the air. When it lands, you reduce that uncertainty. So there's this kind of inverse relationship between information and uncertainty. And in fact, reducing uncertainty is simply another way of defining information. Okay, so let's go to the board and we'll kind of formalize this a little bit. Okay, so here we have a more formal definition of what I just explained. So we've got a system that can be in two states. In this case, this system can be in a state we call 0 and a state we call 1. It's the same color. It's not going to work. State 1 and 0, or we actually labeled them here, state 1 and state 2. We've also used the blue and the yellow to label these states. It doesn't make any difference whether you call them state 1 and state 2, 0 and 1, blue and yellow, or even we could even decide that we're going to call these heads and tails, just like a coin. They're completely 100% equivalent. The important point is that the system can only exist in one of these two states at any point in time, and it can flip between the states. And when it selects between one of the states, it generates a single unit of information, arguably the most important unit of information, the bit. So the bit is a unit of information that's defined by a system that has two states and that can exist in one of those states at any point in time. So this is why binary code is a series of ones and zeros. Each one of these digits can either be a 1 or a 0. It can be a 0 or a 1, 1, 0, 0, 1, 0. And each one represents a single bit of information. So we've got 1, 2, 3, 4, 5, 6, 7 bits of information, with each digit representing a single bit. Now, another point that I have highlighted here, which is also crucial, is at the bottom here. So selecting one state rules out the other state. So because the system can only be in one state at a time by definition, when it exists in one state, it rules out the other state. So it cannot be in the other state. So in the case of the coin, or this more generalized two-state system, when it selects, for example, state 0, it rules out state 1, and vice versa. When it selects state 1, it rules out state 0. That might seem kind of obvious and unimportant, but it will become extremely important later on, because a single state can actually, the amount of information encoded by a single state of a system will depend upon how many states it rules out. So this, again, is a little bit abstract. So let's give another example. So in the case of the coin, when the coin lands heads up, for example, it rules out tails. You've gained a bit of information. Now let's take a dice. It has 6 sides. Let's say the dice lands with a 6. Now, how many states has the dice ruled out by landing on a 6? Well, it's ruled out 5 states, of course. So 1, 2, 3, 4, 5. Those sides have been ruled out by landing on a 6. So even though landing on a 6 is a single state of the dice, it contains more information than the coin landing in a single state, simply because the coin can only exist in 2 states, whereas the dice can exist in 6 states. What about a roulette wheel? So I actually forget how many. I think 30, is it 32 plus 0? Let's go with 32, even number. So a roulette wheel has 32 numbers plus 0. So when the ball, the casino guy, is he a croupier? Is that just cards? I don't know. Anyway, the guy in the suit, yeah. And he drops the ball onto the roulette wheel, right? And it lands on a number. It selects a state. It selects a single state of the roulette wheel. So it lands on the 0, for example. Now, how many states does it rule out? Well, it rules out all the other numbers, all the other 32 numbers on the roulette wheel. And so that state 0 in this case, the roulette wheel contains a lot more information than the 0 in our generalized binary system, where it's just going to be 0 or 1, for example. I referred earlier to the idea of surprise, and that information is related to the idea of surprise. And this is a good point to actually introduce that concept. So if I asked you to guess whether, when I flipped a coin, is it going to land on heads or is it going to land on tails? If you got it right, you're not going to get a round of applause. You're not going to get a medal for that, because it's literally, it's a flip of a coin, right? It's 50-50 chance. It's not very surprising that you got it right. If I asked you to guess which side, when I rolled the dice, what number is it going to land on? You guess it correctly, 6. I'm slightly more surprised, but again, it's nothing to write home about, right? If I asked you to guess which number on a roulette wheel the ball is going to land, and you say 17, and it lands on 17, then you're going to be pretty surprised, because that's, it's much less likely, right? So the idea of surprise is related to information. Okay, so let's go a little bit further now with this idea. I want to show you how putting together systems that can encode small amounts of information, such as a coin, for example, which we saw only can encode essentially a single bit of information. You can put together these very simple systems to encode large amounts of information. So intuitively you understand that, because you know that a computer can use very long strings of these binary digits to generate vast amounts of very, very complex information, and computers are doing that all the time, generating billions of bits of information. So let's start by looking at a system that contains more than just two states. We'll take an example of a chessboard. Because the chessboard has it's 8 by 8 grid and it has 64 squares. So let's look at a 64 state system and see how much information can be encoded, assuming that we can only select one state. In other words, we can only select one square of this 64 state system. Okay, so here we have our 64 state system. So it's a simple 8 by 8 grid, 64 squares. Don't worry about this. We'll talk about this in a second. So what we're going to do is select a single state from this 64 state system. In other words, we're going to select a single square. So let's do that. So we'll select this square here, labeled with blue, and then we're going to find out or calculate in a visual sense how much information is encoded by that square. So the way we're going to do it is we're going to split the board in half sequentially like this, and then we're going to ask a yes or no question. So we're going to say, is the blue square in the left-hand side? And this is where I'm always going to choose left and top if there's a choice. There's always going to be a choice between obviously asking is it that side or is it that side. I'm going to always choose the left or always choose the top when we split it horizontally. So in this case we'll say, is it on the left hand side? And the answer of course is yes, which means we can rule out the right hand side. We're then going to split it again, and we're going to ask this time, is the square in question, our blue square, our selected state, in the top half? And the answer again is yes, so we can rule out the bottom half. We're then going to split it again. Is the blue square on the left hand side, in the left half? The answer is no, so we rule out the left hand side. Is the square in the split it again. Is the square in the top half? The answer is no, so we can rule out the top half. Split it again. Is it in the left-hand half? And the answer is yes, so we can rule out the right-hand side. And then finally, we'll split it again, and we'll simply say, is it the top square? And the answer, of course, is yes, which means you rule out the bottom square. Now, we have found the square with a certain number of yes-no questions. A yes-no question is, of course, the same as a heads or tails. It's the same as a 1 or a 0, plus or a minus, a blue or a yellow, etc., etc. A yes-no question gives us 1 bit of information. And in the bottom here, you'll notice that as we answered these questions, I was writing out a string of binary digits, 1, 1, 0, 0, 1, 1, yes, yes, no, no, yes, yes. So the square in question here encodes 6 bits of information. And in fact, you can encode the position of the square within this 64 state system using this string of 6 binary digits. So we can say that a 64 state system encodes 6 bits of information. Okay, so why is that important? It's important because finding 64 state systems is quite difficult and complicated in the real world, right? If you want to encode 6 bits of information, finding a 64 state system, it might be quite tricky. You need something much more generalizable. Now, the binary coding system is much more generalizable. So rather than having a 64 state system that can encode 6 bits, you simply put 6 single bit systems together to generate a system that can encode 6 bits of information. Okay, hopefully that makes sense. So when we apply this later to the brain, we will see how the brain puts together an extremely large number of information generating units, not bits, but related, to generate vast amounts of information, and that information is experienced subjectively as your reality.